Science for Pigeons. Materials. Solids, liquids, gases. Matter exists in three common states. These states are solid, liquid, and gas. All matter consists of particles. The state of a substance depends on forces. These forces attract particles together. State changes with temperature. It also changes with pressure. Each state of matter has distinct properties. Solids have a definite shape. They also have a definite volume. Solids usually have a high density. They cannot easily be compressed. And solids do not flow. Liquids have a definite volume, but they do not have a definite shape. A liquid conforms to its container's shape. They have a medium to high density, usually lower than the solid phase of the same substance. Liquids cannot be easily compressed, but they flow easily. Gases have no definite volume. They also have no definite shape. A gas expands to fill its container. They have a very low density. Gases are easily compressed. They also flow easily. Particle theory. Particle theory is a useful model. It explains how matter behaves. The particles themselves do not change. Their arrangement changes with energy, and their movement changes with energy. Solids have tightly packed particles. Strong forces hold them together. Particles form a regular arrangement. This structure is called a lattice. Particles vibrate in fixed positions. They do not move around. This gives a solid a fixed shape. It maintains a fixed volume. Solids resist compression, as their particles are already touching. This also explains how they have a high density. Liquids have closely packed particles. The particles touch each other. They form an irregular arrangement. Weaker forces hold them together. Particles can slide past each other. They move in random directions. Liquids flow to fill a container. They form puddles under gravity, as they flow to fill a container from the bottom up. They maintain a fixed volume. Liquids resist compression. Though they flow, there's no space between particles. This also explains how they have a high to medium density. Gases have widely spaced particles. Forces of attraction are negligible. The particles move quickly. They move in random directions. The particles collide with each other and also collide with container walls. Collisions cause gas pressure. Gases have no fixed shape. They expand to fill any container. Large gaps exist between the particles. So gases are easily compressed, and they have a very low density. Particle theory explains gas pressure. Pressure is caused by collisions. Particles collide with container walls. Each collision exerts a tiny force. The combined force creates gas pressure. Pressure changes with temperature. Heat increases kinetic energy. Energy makes particles move faster. Fast particles hit the container walls harder. They also hit the walls more frequently. Harder hits increase the pressure. More frequent hits increase the pressure. All of this, though, assumes a fixed volume. Pressure changes with volume. Decreasing volume increases pressure. Particles have less space to move, so they hit the container walls more frequently, and more hits means higher pressure. Particle theory also explains diffusion. Diffusion is the net movement of particles. Particles move from high concentration. They move to an area of low concentration. This happens in liquids and gases. Think of a drop of ink in water. Spreading smells also demonstrates diffusion. Think of a spray of perfume in the air. This process is surprisingly slow. Gas particles collide with air particles. Collisions change their direction. The random paths slow the spreading. Physical changes. Physical changes alter particle arrangement. They alter particle energy. The particles themselves remain unchanged. Chemical properties remain unchanged. State changes are physical changes. They are fully reversible. Melting happens when solids heat. Particles gain kinetic energy. They vibrate more vigorously. Vibrations overcome forces of attraction. The melting point is reached. Particles break from fixed positions. The solid becomes a liquid. Boiling happens when liquids heat. Particles gain more kinetic energy. They move even faster. Fast particles overcome forces completely. The boiling point is reached. Particles escape the liquid. The liquid becomes a gas. Mass is always conserved. The number of particles stays the same. Heating curves show these changes. They plot temperature against time. The graph rises as particles speed up. The graph flattens during a state change. Flat sections represent melting or boiling. Energy is still being added. This energy breaks into molecular forces. It does not increase particle speed. Temperature measures particle speed, so temperature remains constant. Cooling curves show the reverse. Gas turns to liquid at the condensing point. Liquid turns to solid at the freezing point. Flat sections appear here too. Forces of attraction reform. Energy is released to the surroundings. Temperature remains constant until the change completes. Atoms and elements. Everything is made of atoms. Atoms are tiny particles. They are too small to see. Atoms are made of smaller parts. The center is the nucleus. The nucleus contains protons. It also contains neutrons. Electrons orbit around the nucleus. They move in layers called shells. Atoms make up elements. An element is a pure substance. It contains only one type of atom. The number of protons defines the element. This count is called the atomic number. Copper contains only copper atoms. Carbon contains only carbon atoms. There are over 100 elements. Each element has distinct properties. For example, copper is a malleable metal, while oxygen is a colorless gas. Every element has a unique symbol. Symbols act as a chemical code. Oxygen uses the symbol O. Carbon uses the symbol C. Some symbols use 2 letters. For example, helium uses the symbol He. The first letter is always capital. The second letter is always lowercase. Some symbols come from Latin. For example, iron uses the symbol Fe, and sodium uses the symbol Na. All elements are listed on the periodic table. The periodic table. The periodic table lists all elements. Dmitri Mendeleev created the first version. He arranged elements by properties. He left gaps for undiscovered elements. The modern table arranges elements by atomic number. Vertical columns are called groups. Elements in a group behave similarly. They have the same number of outer electrons. Horizontal rows are called periods. Periods show patterns across the table. Group 1 contains the alkali metals. These are soft, shiny metals, and they are highly reactive. Reactivity increases down the group. Lithium is at the top. Lithium fizzes gently in water. Potassium is further down. Potassium catches fire on water. Rubidium is near the bottom. Rubidium explodes instantly. Group 7 contains the halogens. These are reactive nonmetals. Reactivity decreases down the group. Fluorine is at the top. Fluorine is the most reactive. Iodine is further down. Iodine is much less reactive. Group 0 contains the noble gases. These gases are extremely unreactive. They have full outer shells of electrons, so they rarely form chemical bonds. Compounds. Compounds contain 2 or more elements. These elements are chemically bonded. Atoms join together. Different elements combine to make compounds. Carbon dioxide is a compound. It's a compound of carbon and oxygen. Particle arrangement defines the substance. Consider single identical atoms. This is an element. Now consider pairs of identical atoms. These are molecules of an element. Oxygen gas forms these pairs. It remains an element. Next, consider different atoms joined together. This is a compound. The different atoms are chemically locked. Finally, consider different atoms mixed but separate. This is a mixture. The substances are not chemically joined. They are easy to separate. Compounds form through chemical reactions. Reactions involve reactants. Reactants combine to form products. The product is a new substance. Its properties are completely different. They differ from the original elements. Iron and sulfur demonstrate this. Iron is a magnetic metal. Sulfur is a yellow powder. Mix them without heat, and they shall remain a mixture. You can separate them with a magnet. Heat the mixture to start a reaction. The iron reacts with the sulfur. They then form iron sulfide. This is a hard grey solid. Iron sulfide is not magnetic because the iron is chemically bonded. Word equations display reactions. Iron plus sulfur yields iron sulfide. Symbol equations show the atoms involved. Fe plus S yields FeS. Formulas show the ratio of atoms. H2O, for example, is water. It has 2 hydrogen atoms for every oxygen atom. Compounds can be broken down. This is called thermal decomposition. However, it is difficult to do. Separating a compound requires a chemical reaction. This usually requires a lot of heat energy. Naming compounds. Compounds form from combined elements. Their names follow strict rules. The metal usually comes first. The non-metal comes second. There are many rules to learn. I will explain just 3. First, when 2 different elements combine, their name ends in "ide", IDE. Sodium and chlorine combine. They combine to become sodium chloride. Its formula is NaCl. Magnesium and oxygen combine. They become magnesium oxide. Its formula is MgO. Other nonmetals follow this pattern. Sulfur becomes sulfide. Iodine becomes iodide. And bromine becomes bromide. Fluorine as well becomes fluoride. Second, when 3 or more elements combine. Suppose one of these elements is oxygen. Then the name ends in "ate", ATE. Copper, sulfur, and oxygen combine. They become copper sulfate. Its formula is CuSO4. Calcium, carbon, and oxygen combine. They become calcium carbonate. Its formula is CaCO3. The 8 at the end indicates the oxygen. Sodium, carbon, and oxygen become sodium carbonate. Potassium, sulfur, and oxygen become potassium sulfate. Magnesium, nitrogen, and oxygen become magnesium nitrate. Third, when identical atoms combine. This does not create a compound. It remains an element. The name does not change. 2 hydrogen atoms join up. They form a molecule of hydrogen. Its formula is H2. 2 oxygen atoms form oxygen. Its formula is O2. These are called diatomic molecules. The di in front means 2. Chlorine, fluorine, and nitrogen are also diatomic. They are not compounds. They are merely molecules of elements. Mixtures. Mixtures contain multiple substances. These substances are not chemically joined. The substances are physically mixed. This makes them easy to separate. Air is a mixture of gases. Seawater is a mixture of salts and water. A mixture retains the properties of its parts. A pure substance is different. It consists of only one element or compound. Pure water contains only H2O molecules. It has a fixed boiling point. Mixtures boil over a range of temperatures. Dissolving creates a special mixture. This mixture is called a solution. Dissolving is not disappearing. The particles become invisible to the eye, but they are still there. The mass is conserved. Add 20 grams of salt to 100 grams of water. You get 120 grams of solution. We use specific terms for solutions. The solid is called the solute. The liquid is called the solvent. And the mixture is called the solution. Let me give you an example. Sugar is a solute. Water is a solvent. And syrup is a solution. We describe how substances mix. Soluble means it dissolves. Insoluble means it does not. Salt is soluble in water, but sand is insoluble in water. There is a limit to dissolving. This limit is called saturation. A saturated solution is full. It cannot dissolve any more solute. Temperature affects solubility. For solids, solubility increases with heat. Hotter solvents dissolve more solute. The particles have more energy. They move apart to make space. Cooling a hot solution does the reverse. The solute can no longer stay dissolved. It reappears as crystals. This is how rock candy is made. Solubility depends on the solvent. Salt dissolves in water. Salt does not dissolve in petrol. Nail polish is insoluble in water, but it is soluble in acetone. Separating mixtures. Mixtures separate through physical methods. Physical methods do not break chemical bonds. 4 key techniques exist. These are filtration, evaporation, chromatography, and distillation. Each technique relies on different properties. Filtration and crystallization separate rock salt. Rock salt is a mixture of salt and sand. Salt is soluble in water, while sand is insoluble in water. This difference allows separation. The method has 4 steps. First, grind the rock salt. Second, dissolve the powder in water. Third, filter the mixture. Insoluble sand stays on the paper. This is the residue. The salt water passes through. This is the filtrate. Fourth, evaporate the water. Heating removes the solvent. Crystals of pure salt remain. Chromatography separates dissolved substances. It works well for inks and dyes. Draw a baseline with a pencil. Pencil graphite is insoluble. Place a spot of ink on the line. Dip the paper in a solvent. The solvent moves up the paper. It carries the dye with it. Different dyes move at different speeds. More soluble dyes move faster. They travel further up the paper. This separates the ink into colors. The final pattern is a chromatogram. Simple distillation separates a liquid from a solution. It allows you to keep the liquid. Evaporation allows the liquid to escape. Heat the solution in a flask. The liquid boils into a gas. The gas enters a condenser. The condenser is cold. The gas turns back into a liquid. The liquid is collected. This produces water from salty water. Fractional distillation separates mixed liquids. The liquids must have different boiling points. Crude oil is a liquid mixture. It contains petrol and diesel. Heat the mixture to boil it. Vapors rise up a column. The column is cooler at the top. Vapors condense at different heights. Substances with the lower boiling points rise higher. Each fraction is collected separately. Purity is checked using melting points. Pure substances have sharp melting points. Ice melts at exactly 0 degrees Celsius. Water boils at exactly 100 degrees Celsius. Impurities change these numbers. Salt lowers the melting point of ice. Impurities raise the boiling point of water. Testing these points proves purity. Properties of metals. Metals appear on the periodic table. Most elements are metals. Metals conduct electricity. Electricity is moving charge. This charge flows via electrons. Metals contain delocalized electrons. These are free to move. They flow between the metal ions. Moving electrons carries current. Therefore, metals make good wires. Metals conduct thermal energy. They transfer heat quickly. Metal particles are closely packed. Hot particles vibrate strongly. Vibrations pass to neighbors. Free electrons also move quickly. They carry energy through the metal. Metals have high tensile strength. They are hard to break. Strong forces hold them together. This allows their use in construction. Polished metals are shiny. Smooth surfaces reflect light. This is called luster. Metals are sonorous. They ring when struck. Metals are malleable. This means they can be hammered into shape. The layers of atoms slide over each other. Metals are ductile. This means they can be drawn into wires. Metals are not brittle. Metals have high melting points. Strong forces hold the atoms. Breaking them requires high energy. Aluminium melts at 660 degrees Celsius. And iron melts at 1538 degrees Celsius. Exceptions exist like mercury. Mercury is liquid at room temperature. Metals have high density. Their atoms are tightly packed. They feel heavy for their size. Metals can form alloys. Alloys mix a metal with other elements. This changes the properties. Mixing atoms disrupts the layers. The layers cannot slide easily. This makes alloys harder than pure metals. Some metals are magnetic. Only 3 pure metals are magnetic. These are iron, nickel, and cobalt. Steel is an alloy of iron. Therefore, steel is magnetic too. Most other metals are not magnetic. Copper and aluminium do not attract magnets. Properties. of nonmetals. Nonmetals are a specific group. They are found on the right side of the periodic table. Hydrogen is the only exception. It sits alone on the left. There are fewer nonmetals than metals. Nonmetals are electrical insulators. They conduct electricity poorly. Electrical charge cannot flow. It cannot move through the structure. There is one important exception. Graphite is a form of carbon. Graphite conducts electricity well, but most nonmetals block it. This makes them useful insulators. They are used for cable coverings. Nonmetals are thermal insulators. They conduct heat poorly. Heat energy moves slowly. Vibrations do not pass through easily. This prevents heat loss. It makes them good handles for pans. Solid nonmetals are brittle. They possess little strength. Weak forces hold the molecules together. Solids shatter when hit. They snap rather than bend. This means they are not malleable. Solid nonmetals are dull. They do not reflect light. Their surfaces are not shiny. They look rough and matte. Sulfur is a yellow solid. Carbon is a black solid. Both are dull and brittle. Nonmetals have low melting points. They also have low boiling points. Weak forces exist between molecules. Little energy breaks these forces, so they melt and boil easily. Most are gases at room temperature. Oxygen and chlorine are gases. Only one is a liquid. Bromine is a red liquid. Nonmetals have low density. Their particles are usually far apart. This is true for the gases. This makes them lightweight. Helium is less dense than air. This allows balloons to float. Finally, nonmetals are non-magnetic. Magnets do not attract them. Only iron, nickel, and cobalt are magnetic. These are all metals. No non-metal is magnetic. Properties of other materials. Polymers have useful properties. Plastics are types of polymers. Examples include nylon, polythene, and PVC. Polymers are electrical insulators. They are also thermal insulators. Energy transfer through them is difficult. Most polymers are flexible. They bend without breaking. They also have a low density. This makes them light for their strength. Lightness enables strong, non-heavy objects. They are easily molded. Manufacturing can achieve almost any shape. Polymers make crash helmets and kayaks. They also make carrier bags and drink bottles. Polymers are specific compounds. They form from many small repeating molecules. These molecules join in long chains. These chains usually contain carbon. Ceramics are stiff but brittle. Ceramics include glass and porcelain. Bone china is another example. Ceramics are good insulators. They resist electrical energy transfer, and they also resist thermal energy transfer. They are brittle materials, and they lack flexibility. They break instead of bending. They are also very stiff. They withstand strong forces before breaking. Ceramics are used for teacups. They are also used for brakes and spark plugs. These uses require high heat resistance. Ceramics are made by baking substances. Clay is a common substance to bake. Composites combine different materials. They contain two or more materials. These materials are stuck together. The combination creates useful properties. Fiberglass is one composite. Its other name is glass reinforced plastic, also known as GRP. It contains glass fibers embedded in plastic. It has a low density, like plastic, but it has high strength, like glass. These properties suit skis and boats. They also suit surfboards. Concrete is another composite. It contains sand and gravel. These are embedded in cement. It withstands high compression stresses. It resists being squashed. This makes it ideal for supporting heavy loads. Concrete is a key building material. It is used in skate parks and shopping centers. It is also used in airports.